the way a superpower is constructed, it's all about the super agent, basically the multimodal agent with which it closely interacts with. It's called the Jarvis, right? So you might have seen the movies where Iron Man, most of the commands he executes through Jarvis. Jarvis is his first multimodal agent, which basically tightly integrated with him and executes every aspect of his maneuvers, whether he's on flight or he wants to activate a weapon or he wants a real-time analytics. All of this is provided by Jarvis. So now we are talking about, to realize this dream and make a reality. What's the first step? Of course, that's still a long way out. But I think XR is really the first step where we are making some kind of a superpower available for every of our users. This superpower will assist them in day-to-day so that they can make the task more simpler and they can focus on more productivity. Right? So that's the context I want to begin with. We all know actually multimodal agents have been in existence for now, and primarily multimodal agents as of now, as you see today, right? What are the capabilities? They can process basically multiple modalities, whether it is image, voice, audio, video, and so on. And adding to that, there is underneath there is a multimodal language model sitting there, large language model, which can basically perform what we call as the perception, reasoning, and also the action. So this gives the power for the multimodal agents to get most of the tasks done more efficiently, as you can see today with the proliferation of so many agents all around us. Now, taking it one step ahead, what we're really looking for is basically capability as of today on the handheld devices, right? So if you look at handheld devices, we already have some amount of capability existing, wherein we can pose a query, we can feed an image, and the agents are able to respond based on the input queries. But is it sufficient? The question is, can they really scale up? Right? For it to scale up, really the agents have to be much more closer to us, and they really need to be accompanying us most of the time. And I think that is truly possible with the next kind of device that we're talking about, which is the XR device. Therefore, I think multimodal agents are very much meaningful in context to XR. They make it more meaningful, and not only meaningful, more powerful. The reason is very simple. If you look at most of the head-mounted devices, so they have the capability to basically continuously understand the real world. So there's a continuous perception that's happening, and it has access to a lot more information than the agents that are existing today on mobile form factors. In fact, it can access information about your gaze, where you are looking at. It can also access information about your hand gestures. It can understand biological signals. It can understand your emotions. It also understands where you are. It understands the spatial environment, where you are located. So this is very rich information. With this much information being fed to an agent, I think we can expect a lot more improvement in the kind of experiences or the assistance the agents can provide. So in some sense, we can see these agents will become spatial companions, and they really start seeing the world the way you are looking at the world. And that also brings us a lot of challenges, right? So once these agents become context aware and they start providing assistance, definitely they bring in a lot of value. We see a lot of applications. Just to illustrate here, there are so many applications we can think of where agents can continuously assess the world around, and they can give overlaid information, which makes the task much more easier. But that also begs a larger question: how reliable are these agents? Are we able to kind of use them without properly evaluating their reliability and accuracy? So that's the biggest question that we and my team are answering here in Samsung. So I hand over this talk next to my colleague Satish, who will take us through the challenges and how we are overcoming. Thank you.
Hello. Thank you for having me. My name is Satish. Before we get into, I think in the first slide, you have seen multimodal large language models. Before we even go a little bit deeper into multimodal large language models, let me take a step back and talk about LLM models, which are actually powering the chatbots today, which can actually take in your query and then process and give you an answer. What they are today, they are really wizards in creating text, creating words. They can actually do your kids' homework. They can prep you for a debate competition. If you do it right, they can actually train you to crack a job interview too, right? And I'm not joking, and I'm not hallucinating. It's really true. But there is no vision in it. So there has to be a merger of multiple modalities to make it a real agent, and that's where multimodal large language model comes in. Now, multimodal large language models, they blend different modalities, and then they actually unify the whole intelligence and speak as one. They are not academic curiosities anymore. They are actually big things in the industry today. If you talk about, it all started off in 2021 with the advance of CLIP. I think you would have remembered that the CLIP model that has come out, where it was actually trying to bridge the language and vision, and then with the advent of models like GLIP and Flamingo, these multimodal large language models have really taken off in the industry. Today, if you look at these models, right, we have GPT-4, we have Gemini, 2.x versions. They really stand tall. Boasting these vision transformer architecture for analyzing the vision to language understanding with the transformer-based relevance. If you actually looked at the first slide, there is a module called Connector, which is actually the heart of multimodal large language models. They actually blend multiple modalities and enable the model to see, hear, and speak as one. For all its excellence, right? These models are still young, to disappoint you. They are not flawless. They have some cracks in their foundations. Let's say the amplified biases across modalities to hallucinations, where they seamlessly blend the fact with fiction, making you really believable in alarming ways. But and also the key thing is evaluation gaps. Right? The evaluation gaps that we have right now, they actually make you wonder if it is true generalization. Right now it is not. So today we'll talk about what are the limitations of these models, and how we'll talk about how these architectures introduce these limitations and some of the data dilemmas that we have, and the benchmarking strategies which actually enable us this true generalization. Are we up to the mark, or do we need some more improvements? So let's just dive in and talk about hallucination first. So now, what is hallucination, right? So when you ask a question, it generally gives an output. When we talk about multimodal large language models, it gives an output in the form of a text or in the form of a generated image. However, if it gives you a text which does not relate to the visual content that is out there, that is actually called hallucination. Now we are talking about multimodal large language models, right? So here computer vision is the key. So most of the times computer visions are mostly object-centric, so we'll talk about object hallucinations. There are two kinds of hallucinations as shown here. When an agent talks about a non-existing object in the scene, that is the first type. The second one is, it talks about something ignoring the existing objects in the scene, which we are not really concerned about because it is not a real harmful thing. But what we are really worried about is the first one, right? Which is when a model talks about something that is not existing in the image, right? It is really fascinating, when we all started off with deep learning. We face these very fundamental problems of data, fundamental problems of architecture, right? And then we had these training strategies, right? Everything, even if we are talking about MLMs, they all boil down to these common problems. Right? So when you look at this data, there are three factors here. We talk about data quality. When we are talking about data quality, these multimodal large language models has two aspects to it. You have an LLM, you have a visual encoder, so you have data corresponding to the visual encoder. You also have data corresponding to the LLM, right? Now, typically this data is huge. They are vast in quantity, but however, if you pitch against the textual corpus that we train these LLMs versus the image text pairs that we train these visual encoders with, it's heavily imbalanced. Right? So what happens there is when it is heavily imbalanced, it tries to fall back on the deep-rooted textual reasoning that it has learned rather than attending to it. Right? So that is actually the fundamental problem that we're talking about when we're talking about LLMs. And that is the first thing that we're talking about. So it's data imbalance. Now, if you have developed these deep learning models, you would have already know that this data imbalance is such a huge thing, even if you want to develop a very small model. Right? And then the next thing is data quality. These models are so data hungry that in order to feed these data hungry models, you will have to fall back on heuristic approaches, right? And of course, heuristic approaches gives you a lot of data, but they don't guarantee the quality of the data, right? So now what happens is you end up with noisy data, which has misalignments, it has these corrupted samples, most of the training samples are inaccurate. Now that is one of the causes for hallucination too. The second thing is lack of diversity. Now, when I say lack of diversity, if you had undergone this training of multimodal large language models, there is a phase where you try to do training or fine-tuning with instructions, right? Now, you can actually classify these instructions into three types. One is the positive instruction data set, which has an instruction, it has an input, it has an output, and the output says that, okay, the model is supposed to behave in this way, right? And then second, you have something called negative instruction data, where you also have an instruction, you also have an input, you also have an output, but the output says the model, this is not how to behave, right? And the third one is reject responses. Now, this is mostly for refusal mode, where you're actually trying to say the model that, okay, the query is very harmful and you can actually refuse to answer, right? Now, even here, when you have this lack of balance in these ones, like for example, usually what happens is you have a lot of positive data, instruction data. Now, when you feed the model with lots of positive instruction data, all it tries to learn is to say yes, and it tries to answer, and it tries to, even though it doesn't know the answer, it tries to fill the gaps, falling back on its deep-rooted knowledge that it has learned through lots of text corpus that it has found. So now what happens is, because of this, that is exactly the case here. So there is always a lot of imbalance that we see. So one way to correct it is to find a balance between all these three categories that I just talked about, which is actually not easy, but this is one of the ways where we can actually prevent the hallucinations. The third thing is statistical bias. Right? Statistical bias is also something, if you are trying these multi-level models or multi-level classifications, if you are trying these, then you would have seen two predominant problems in that criteria. One is most highly frequent objects appearing in your training data. Like for example, let's say in your training data you have a human presence in most of the images. Now during inference, you show an image that doesn't have a human, but it says that, okay, there is a human present, because it sees a lot of, it picks up a lot of bias during this training. So it thinks that during inference also there is a human present, right? And the second thing is co-occurrences, right? So co-occurrences is, I'll give you an example now. If you actually train your data with images of kitchen, let's say, right? So kitchen actually comes with certain objects like your refrigerator, your microwave oven. During inference, you feed an image of a kitchen which has only microwave, it doesn't have a refrigerator, and ask if there is a refrigerator. Naturally tends to say that, yeah, there is a refrigerator, because it learns those co-occurrences, right? So it assumes that, okay, there is a microwave, it's a kitchen, so it assumes that there is a refrigerator. But actually in the content, this is actually hallucination, and that is first kind of hallucination. Now, the second one is the model itself. Like we already said that there are two models to it, the vision encoder and language model. Now, the language model here is too strong, right, because it has lots of data, but we don't have this in terms of vision encoder. So what happens here is when you are trying to generate a response, now mostly it falls back on the textual prior that it has seen rather than attending to the visual content in the image. That is one form of the hallucination. Now the thing is, if you are to eliminate these hallucinations, one of the ways is to actually do the training right. Like for example, the training and inference. One of the ways is you actually break the training into pre-training stage, and then you have this instruction fine-tuning stage. Get your objective functions right if you are to avoid these hallucinations. Like for example, one of the most important things is visual hallucination. Visual grounding. Now, if you don't follow visual grounding during the pre-training stage, you end up with lots of hallucinations. I'll give you an example. The other day, I was actually trying to search for a research topic, a certain topic. Usually, I go to Perplexity or I usually go to Gemini to get me some references of some research papers that are out there in the community. But this time, I thought, okay, let's explore DeepSeek. So I just asked DeepSeek, get me some list of papers, and of course, it threw me a bunch of papers. And I was just scrolling through the list of those papers, and I came across one paper. It mentioned the name of the paper, and it also mentioned the authors of the paper. Surprisingly, I thought, oh, this is exactly what I want, because this is exactly what I was searching for. When I looked for the paper, this was completely non-existent. It really fooled me. It's completely hallucinating, right? And the paper was, it's not there, right? And then I went back and then asked DeepSeek, can you please get me a link? And then it went round and round and round, and then came back saying that, oh, this paper is not there. So this is what we are actually looking at, right? Now, let's talk about this visual grounding. We have actually mentioned about visual grounding, right? So visual grounding is a task where you actually try to localize an image depending on the phrase description, right? Now, there are several types of visual grounding that are there in the literature. One of the things is classical visual grounding, where you actually have a complete phrase and you're trying to localize to a particular region in the image. The second one is phrase localization, which is actually very important, where you try to break your phrase into several entities and you try to localize every entity to a particular region in the image. And the third one is generic visual grounding, where you have a phrase and you're trying to ground it to multiple places or multiple objects in the image, or there are no objects at all. So if you take care of all these kinds of visual grounding techniques in your training, you can actually avoid these hallucinations. Because one of the main reasons that I actually talked about in the previous one is when the language model goes haywire, right, and it starts to ignore your vision model. That's when hallucination. So this is the root cause of this hallucination, right? And the third one that I want to talk about is abstract visual reasoning. Right? You can actually see certain images here, and any same human, if you look at these images, they can really solve these puzzles instantly, right? Now, you have these benchmarks to evaluate these multimodal large language models, and they really exceed all the human capabilities with these benchmarks. Like for example, your text and captioning, your image generation, to video understanding, it really outperforms human capabilities. But this is one area where it is really, really lacking, right? So you can see that it has a certain way of solving these kind of puzzles. Now, one of the things, you can look at all those 5 steps that I mentioned there. It needs to look at all those 5 steps, follow those 5 steps. So it is almost like you have to derive an analogy across several images, and then you have to derive the roots, and then apply the root to get an answer, right? And that is exactly where we are failing right now. And why? Because the first thing is we have an architecture limitation. we have something called as a sequence phenomena we have that we feed to our transformers. The second thing is when it comes to language, we fall back on statistical association. It's all statistical model. And when we talk about visual encoders, it's all about pattern recognition. But let's ask one basic question, which is, why is this abstract reasoning really important? Because we want to move from seeing and explaining to seeing, inferring, and then explaining, right? It's not just seeing and describing that we want. We want some serious human-like generalization, right? And that is where we are heading. And this is one of the main factors to even get there. We are not there yet, but we are in the right direction. Okay, the last thing is, if you want to really deploy a model, you really have to evaluate and benchmark, right? And the benchmarks that we have right now is a fragmented landscape. So what I'm talking about is, you have benchmarks for certain narrow tasks to test the models, but we don't have a holistic benchmark, right? Like for example, you see there is a benchmark for DQA, and it only tests and evaluates only on the DQA. Right? And we have something called video and temporal understanding, where we have Ego 4D. It only tests and evaluates on egocentric footage that is completely made for embodied AI research, right? But we don't have a holistic benchmark, and that is exactly what we need. And we're not there yet, but we are progressing in the right direction. And Biplab here will take you through some of the methods of evaluation. We'll take the question at the end.
So, I think I'll keep it short. Mostly I'll go into the details of how we evaluate, mostly only like that. So, idea is that, like Satish was telling that hallucination is very important in multimodal. So, what we'd like to do is we'd like to have some way of evaluating this model. So, research community has come up with many such benchmarks. And there are other benchmarks which are basically collating out of them. So VLM evaluate is something that we are using. So this is a way to evaluate the multimodal elements in different scenarios. So idea is that most of the frameworks, they have this kind of, there is this data set. So there will be lots of data set, like VLM evaluate has more than 20 multimodal benchmarks or data sets, and we download them, process them. Then there will be some task evaluated. So there will be different tasks like ATP, visual symbolization, and then other tasks. And also, what we will do is we will have sets of multimodal elements and we'll benchmark it. And after that, each of them will be presented in some kind of leaderboards that you can evaluate. So there is something called Open Compass, where the VLM kit is hosted. So what you can do is you can see which of the best performing models are in the leaderboard, as well as many methods. What we can do is we can actually see the reasoning of the wrong or right evaluation. Sorry. So this is one example from the benchmark, that is LM style. So this is, the idea is that we like to evaluate across many scenarios. The main thing that we like to do is that we evaluate on, say, in MM style, so this is one of the benchmark that, so like in the previous VLM kit, there were more than 20 benchmarks. So MM style is one of them, and it was published in UX 2024. The key takeaway is that evaluate MLMs across various dimensions. So one important thing that I like to mention is that all of these data sets, they have a ground truth defined. So which is limiting, because even if there are many scenarios which are covered, there will be always scenarios which we haven't taken care of. So the idea is that why not use MLM as a judge? So the idea is that we will evaluate the MLM with another MLM. So it's like what we'll try to do is that we'll try to create an agent which will be a judge agent. So this gives an overview of how we are trying to do it. So we'll collect instruction image pairs. So this will not have the ground truth. So ground truth, by ground truth I mean is like will not have the actual what is the expected answer. So that expected answer, if human is providing, that's very costly. So what we are doing is that we are having another LLM, so which we call as judge LLM, and that judge LLM will be evaluating it, and it will be evaluated across different kinds of scenarios, like scoring, pair comparison, and ranking. So these are the examples. Like if you directly give the score, that's judge giving the rating directly. If you have two answers like coming from two MLLMs, then we call that pair comparison, and the third one is like you rank multiple LLMs based on that answer on the same question. And one idea is how we evaluate this LLMs. The judge LLM, when we have those LLMs, we try to take Pearson correlation or some correlation, but we want to see whether the email is actually the same as the MLM. So this, I'm not sure if it's visible, but overall idea is that we use LLM using one of the methods is vanilla prompting. So the latest models that are there, like open source as well as non-open source, what we can do is like we can just provide a instruction that okay, 0 is completely incorrect, then 1 partially, 2 slightly better, and then 5 is the perfect answer, and it covers everything. And you can define the different dimensions of the correctness. So based on that, so this is basically giving how we'd like to evaluate it. So it's a basically prompt engineering task, but we have to adapt it for a judge. So how do you do if your prompting is not good enough, then we can do fine tuning. And by fine tuning, what I mean is like we'll just take the existing LLM, then we'll do. So there are few steps when you train multimodal LLMs. The first step, like Satish has mentioned, is that we do the pre-training. And after pre-training, once we have a model that is tuned for multimodal agentic AI tasks, we can fine-tune it for judge agentic tasks also. The first thing that we can do is we can do supervised fine-tuning. So I'll skip this because I think you guys might have already gone over it. The second thing is the reward model. So this reward model is the same as the RLHF that you might have already seen. So the idea is that the same reward model can be used for judgment. There are works like visual PRM where they try to have reward for each step, and then we can actually efficiently make this better also. So I'll just go to examples. So this is one example where user is asking how many umbrellas are there. Actually, there are 2 umbrellas. So the agent here we use Gemini 2.5, and it was telling that it's good, and gave a rating for it. The next question that I asked was slightly like Gemini knowledge base was maybe the 2.5 version was not aware of it happened. So like this is actually the rating. So it's like whatever the things I do. But there was this. This is something that you can see like it's a kind of hallucination. I asked who owned the women's if it was the printing club. It was India. But here, because the training data, whatever it was, there was some cutoff. It was telling that it will be September, October, and then based on that, the judge gave you can actually go over the reasoning there. So what we did is we actually did some fact checking where we actually searched few results and found that there are 2 articles which is telling that India had won the World Cup. That's why the hallucination is so any questions we can take?